Chapter 10, Lecture 10, Dynamic Binding Polymorphic Methods. Dynamic binding. We talked about this earlier, but here we would like to look at the mechanism for this concept. We learned about static binding and the dynamic binding. Static binding is at the compile time, you know which function body you will execute. Dynamic binding is the virtual function resolution. You try to find its execution body at the runtime. So here we have a main program, and then we have flu class and then orange class. So basically your flu class is a parent class, orange class actually is inheriting it. And then you have 3 flu reference, the parent class reference, and the base class is the flu class. You have the if function, you have the PO function, set color, and the color function, and actually you have the V table. And the derived class, you have orange constructor, deconstructor, and if function. So this if function actually is polymorphic. This set color actually is a method that actually is shared. So right here, if we run the if function for flu1 and flu2, if function, it will go to this V pointer and then get the implementation body from here. And then because the reference 1 is actually flu object and then flu point reference or flu pointer. And then the second one is orange class. It's orange object and then flu reference. So it will find its V pointer over here and then find the V table from here. And if you use the PO function, the PO function actually has definition over here. So actually, the PO function, it will actually get an implementation body different from it will actually let me see. Here you have the flu1. You have the color and the field, color and field on each one, and these data are actually from the data class. So PO function actually is a shared function defined over in here. So this one, it will go through for this flu2, the PO, you go here and go to array table, and it will go to here to get the body from the parent. And it doesn't have the definition from itself. And flu2, again, is actually go to the V table, and then we'll go to V table here and get the copy from here. And for flu2 color, the color function is actually will only get its normal static binding through here. Because the derived class, the orange, doesn't have a definition. This is called a dynamic binding. Basically, you will runtime check if there is definition, if a function being override by the orange class, And it's a function that actually it has implementation, and the parent also have implementation. Then it will go through the vtable and then find the local copy to run. And if the parent doesn't, some function parent doesn't have the definition, it will be done by the current class. But if the object is actually parent's definition only, then it will easily go to the parent class. Because this flu2 actually is of the flu reference. So you consider this flu2 or which actually the object is this type. By reference, it's actually the flu type. So you will get to the static binding and get the copy from the base class. So vtable is one way to implement this dynamic binding that's used for C++ language. So typical implementation of vtable is created for every class that declares one or more virtual functions or override a virtual function. Such class is called polymorphic class. And in C++ language, polymorphic class need to be explicitly using the vtable and vfunctions. But some language like Java doesn't need that. Function override virtual functions from a parent class are just in the vtable of the derived class. So through the derived class vtable, you will find the right copy, and the function is called and resolved at the runtime from matching index in the vtable pointed by the actual object's vtable. So vtable actually the object has a v pointer. The object itself has a v pointer, and because you declare the function to be v virtual function, you will have that v pointer in the derived class, and you will easily go through that and then find it here, and then you will resolve whether there is a copy of the functions like it. You will go to here. If there is no definition for PO, you will go to here, even though it's declared as virtual function. It will also depend which copy you will get, depending on whether you have the definition of the function or not. And that's defined in the derived class. And each object of a polymorphic class has its own v-pointer, but there is only one v-pointer per class. V-table and the v-pointers are added by the compiler and not visible by the programmer. So here we have this polymorphic method, and let's look at the code. Your flu class, you have a if function, you have the PO function, and then both of them are virtual. So since it's virtual, it will be defined in the vtable of this flu class. And the implementation body right here, you have a copy for the flu class. On the other hand, this orange class, it actually extends flu in public way. So in public way means you can use the function it and also for the PO. But right here, it overrides the it. And then because it overrides if function, and then because it actually is a virtual function, so at runtime, for the v pointer in the object, it will directly go to this copy. But for the PO, it doesn't have that. In the vtable, it will go to here to find this copy. Subtype polymorphism. Subtype polymorphism is also called as inclusion polymorphism. Your subtype is actually through the is-A relationship, and is-A relationship actually is kind of a membership. Orange is fruit. So orange is a member of fruit. So that's called subtype polymorphism. A person, the class student, actually is then person class publicly, and professor is also a person. So we have the inheritance structure like this. So right here we assign, we actually create two objects over here, and then we assign the ages to two pointers, and those pointers are person type. Those pointers are person type, and we have base function print label, polymorphic function print labels, and static dynamic binding for print labels. So these two are different, and because student has students print labels, and person has the definition, and then professor has its own definition for print labels. So let's see. If we actually run, run the student object, we know it's the student object. We will actually go to run like this. Okay, and professor, we will run like this. And then, but if there is a variable we don't know which object it is, and it actually declared as person, then we will need to know what copy it would run. So here we need to check the overriding rule to find out which version it should run. So semantical performance, the principal argument against the static method binding is that static approach denies on the derived class control over consistency of its own state. So suppose the example that we are building a I/O library that it contains the text file. So here is the text file. You have the seek function, and here we have a class that actually is a subclass called read ahead text file. So right here we have a text file class, and then inherited by this read ahead class. And there is a seek function, and it actually is a redefinition. So seek function actually here has a copy, and then here is different copy. So the code read ahead and seek will undoubtedly need to change the value of the upcoming characters that actually is for the different device. Say 80 characters per line or 132 per line. So if the method is not dynamic dispatch, we can guarantee that this will happen. And if we pass a reference to a subroutine, expecting the text file reference as argument, and that subroutine called seek, we will get the version in the base class if we don't override it. And we may not like it because we would like to have the copy in the read ahead text file format. So that whether you use static binding or dynamic binding, need to be careful. Virtual and non-virtual methods. A virtual function or virtual method is an inheritable and overridable function all methods which dynamic dispatch facilitated. So a dynamic dispatch is through the V table and the V pointer. Call to virtual methods are dispatched to the appropriate implementation at runtime based on the class object rather than the type of reference. So it's basically based on the class of the object, not the type of reference. So basically you will have fruit. It actually will depend on the object type, not the reference type or pointer type. A.95 programmer associate it with certain references. In our mailing label example, a formal parameter or access variable can be declared to the class Y type variable. It will be declared to be of the class Y type person's class, in which case all calls to the methods that parameter or variable will be dispatched based on the class of the object to which it refers to. So basically, it will depend on the object, not on the reference. So for example, if we pass through a person, and that person is reference type is person type, but it may be student, may be professor. So that print label will actually be polymorphic. But if these two, you pass through a student's copy, and that is student class, it will only allow student to process, because person actually is a superclass for student and for professor. So these two will get the local copy. So here, if we use the person's class reference, and if for this, it will call appropriate overloading method version by the dispatch depending on the type of the R at the runtime. And that actually is, you need to put something like this, person's class, instead of the class specific assignment. It actually will provide the polymorphism through such arrangement, and you will go to the right copy. But if you declare a print mailing label, it will actually go through the copy that you define in the class. So here is a method that used to dispatch. Abstract class. C++ refer to abstract method as pure virtual method. Pure virtual method is abstract method. So that's the terminology for C++. And here we can have the abstract, that's in C#. But in C++, it would actually set it to 0, so no implementation. That assumes that the function equals 0 is no implementation, and that is actually declaring that function to be abstract. And it must be virtual because there is no implementation, so you actually need to find the body in the subclasses. So this make it a abstract method. And since the method, this class has a abstract method, the class itself become abstract class. But actually in C++, there's no such modifier or ID to differentiate a abstract class or a concrete class. So it actually would be better that you, in your name, you actually call the class called abstract person. or sometimes call it general person. That will actually be better because C++ there is no such thing as abstract class by the programming by the language mechanism. So, but Java do have, or C#, Java do have that, and C# do have that. So abstract class, no instantiation, serve as a base for concrete class. So it's impossible to declare an object of a this type, but it can be used as reference. So you actually, on the right hand side, you can new using the object class. No, this is not okay. On the left hand side, object class as a reference, that's fine. This side is fine. Object class, you can have dog and three different kind of the dog, and that is called object class. And you can have an interface. By interface, actually use the implement, and this is in Java language. In C++ language, there is no such thing as object class or interface, and that actually you can use the virtual method and pure virtual method to implement object class. And if the object class has no data field and the abstract method only, and that will be a interface. So actually here is the relationship between using of the class, interface, and object class. So here in C++ language, you actually are all classes just by the definition of using the pure virtual method and the virtual method to define whether a class is abstract class or interface. And a widget type 1 or type 2 that can actually extend a object class and actually can also implement some interface at the same time, but there's no way you can actually have multiple interface, but you cannot have multiple object class or class. That's not allowed. That's in Java language. Dynamic method binding number 2, finding the method implementation. So member lookup, memory organization for dynamic binding. So here we talk about the mechanism of how to find members. So writing static method binding like C++, Similar, C#, 8.95, the compiler can always tell which version of the method to call based on the type of the variable being used. If no virtual method declaration, you will find the static version by default. And then, so basically it's a default static without further specifying, and actually exceptional virtual for dynamic, and virtual may also still find its base class copy. In Java, it actually, without telling, you will actually check the reference type and then find the dynamic copy. So Java actually is default dynamic. So technique, you use a vtable, virtual method table, and we explained the vtable before. So here, let's look at the implementation for this vtable and vpointer. So we have a full class, and it has a bunch of the virtual methods. And here we have the full object. So here is a virtual table defining the K method, L method, M method, and N method. Okay. So here, for example, if we have a call to F M method, it actually will basically load this one, the full object location, and then find the body that would be the virtual table address. Okay, so you get this virtual table address, and then you calculate this number. That's 4 is size of edges. So each edges you have 4. So you have this M is like 3 minus 1 is the number 3 function minus the number 1 function's location. So that 2 times 4. So you actually jump by this much, and then you have the R2's body. R2's body is actually, this one is the R2 location, and this R2 is over here. So R1, this one actually is R1. Through object's location, address is put into R1, and R1's body is actually this through virtual table. And then you actually use that table content and then calculate this, and you assign back to R2. So R2 actually being updated by here. You will go to this location to find the body. So that's the assembly to find the virtual pointer and to find the function's body. Implementation of single inheritance. If bar is derived from foo, we place the additional field at the end of the record it represented. We create a vtable for bar copy in vtable from foo. So if we have a class foo over here and a bar over here, so we will copy the vtable from foo object as from the base. We actually will copy actually the vtable from the base one, and then edit 2 function from bar function. So actually M is override, and then these 2 are actually virtual function. So here it will get to the dynamic function through this vtable over here. So you, for bar class, you will actually copy from foo for a vtable over here, and then add your own virtual function in here. So you will have a bigger table. But if this bar object, say we have a bar object, and then you declare it as a full reference, and in that case, these 2 functions will be disabled. You will act like a full object and find dynamic binding over here. But these 2 features of the bar object, if you run B, that is function S, it will not be allowed. But if you have a B.M, it will be allowed and finding the dynamic copy. So dynamic binding of downward assignment and upward assignment. So basically we have a full class, bar class, and full object, and bar object. And then here we have a pointer of the full type and the pointer of the bar type. And then we copy the address of, that's an object of this one is full type, and assign to a pointer of full type. We have the object of bar type assigned to full type reference. So the function in the bar object will be disabled, and using it will become a full object. So static semantic error F will this one actually is an OK reference to Q. We'll use the prefix of the B data and the virtual table. But here, if we assign the address of a full object to a bar pointer, that will create semantic error. So this one is not allowed. For parent object to child pointer or child reference, that is not allowed, or pointer. Casting in C++. C++ allow backward casting, so you actually can use like dynamic cast operator to cast back from the this is full type pointer back to bar type pointer. It can recover the feature in the bar object. So backward compatibility C++ also supports traditional C style casting, and you can have this dynamic casting, and you also have the static casting, something like that. Okay, and actually that's C++ way of casting, and the C++ way is safer in some sense, but will be not as easy to use. So it's permitted but risky. Okay. So C-style casting is up to the programmer to ensure that actual object involved is of appropriate type. No dynamic semantic check need to be performed. So actually use that with carefully. So dynamic binding in Java and C#. Here is a dynamic binding for Java, and you have this function called you have this class called polymorphic demo, and you actually have right here you have you have a person. So person is inherited by student, and student actually and person inherit object, and then you have graduate student inherit student. So the method take a parameter of object type over here. For this method, you actually M method is over here is a polymorphic method. So you can take a graduate student or person or object, okay, and then you perform different version of the toString. An object of subtype can be used wherever its supertype, the parent type is required. This is called polymorphism. And then when the method M of object is executed, the argument X to string method is invoked. S may be an instance of graduate student, person, or object. And this will find its own copy and done by virtual machine, the Java virtual machine. And this capability is known as dynamic binding. And dynamic binding in Java and C# actually is using the thing called the dynamic binding chain. So basically, your object is of Cn type, and Cn actually your child class is of the C1 type object, and C1 inherits C2, inherits C3, and then the Cn is actually the object type. So basically, you will try to find the local copy from C1 to Cn. If C1 has implementation, it will go C1. If C2 has implementation, it will go C2. Something like that, one by one. So that's your dynamic binding chain. The first form closer to your object will be called, even if your reference is of the great parent type. So reverse assignment in Alpha and the C#. This question mark is dynamic, equal is assignment. So Alpha have a reverse assignment of the this question mark equal, which is like C double plus dynamic casting. So that's a recover function, and you put a question mark. So here you have a full and bar, and then you have the bar assigned to this full. That actually is a conversion from a shell reference to a parent reference. That's always okay. But the reverse one, you need to use a question mark that will perform the dynamic assignment casting checking. Dynamic method number 3, binding number 3, object closure. So object closure is talking about a function as pointer. So review of the object closure. Right here we have this one should be Java type. So you have interface in function, and that one has a call function, and then you have a class plus X that implement the in function interface. So we have a constructor, and then there is a overriding function called call. So here we create an interface F that's holding a +1 object, and the constructor actually send the 2 for the X. So actually it will have 8. This one will be configured to 2, and then later you call F dot call 3. Actually you pass the I equals 3 over there, and then you will return 3 plus 2, and it will print 5. So the in function the in function interface can be inherited by plus function, minus function, multiply function, and the whole function will have different flavor. You can do using the plus function, subtract function, or multiply function. So actually that interface F actually a long time will determine which function it will be used. And that actually if you do pass F as a reference to a certain function, to set executor, and then do call, it will actually pass in the function and use that object closure as the function closure. So you can use a reference of the in function type as a pointer or reference to the different functions, dynamically dispatching different function to run by using the reference and the call function. So this is a dispatching of a function of different type using the function closure. So object closure, right here we have a object closure. In this one should be in C++ language. Virtual method in object closure using polymorphism to pass methods. So right here we have a template for the unit operator. Okay, and then it has the operator been declared as an object. And then here it should know that this mechanism rely on the dynamic method binding. So here an object closure can be used in the object-oriented programming language to achieve the same effect as subroutine closure. Okay, anyway, let's look at the code. We have this array, integer type array, and then we apply to A, we apply this plus x2 function. So here is a function, and then we will apply to A. And so this actually plus 2 can be of, say, we can have the multiply x with 2. Then you will pass different operator using the apply to A function to apply different function over there. So right here, when you call this one, you set up this plus x2, so n being passed to here, okay, by the constructor, and then it's actually set up the operator. So the operator is of different type. You can actually return different type. It can be a integer type or different type. So right here, you call that, and then you apply function. You have unit operator f alias. So actually, you pass in this this function to there, and then you pass the array to be like this. You pass to here, and then you have the size of the array. You pass 10 here, so 10 being passed to here, and then A will be passed to here, and then that's your A array. So here we had a f function. The f function is plus x2. That will be applied to the array A, I. So with that, you actually will be calling this function through here, and then actually get executed for this. So over here, we are setting up a apply to A function that can actually apply a certain operator to a certain array, and for that array size of A, that's a function of this apply to. So this apply to A is a dispatcher function that will find different class plus x to do that, and this class unit up is actually like a abstract class or interface. In this case, it actually is an interface. But C++, there's no such language mechanism of the interface type. So you actually use a class with pure virtual method or abstract method. Encapsulating arguments, a particular useful idiom for many applications is to encapsulate a method and its argument as object closure for later execution. So, for example, that we are writing a discrete event simulation, we might like a general mechanism that allows us to schedule a call to an arbitrary subroutine with arbitrary set of parameters to occur at some future point in time. If subroutine we want to have called vary in their number and the type of parameters, we won't be able to pass them to a general purpose schedule at routine. So let's do this. Actually here we have a function call. That's actually this one should be the function call should be a interface. So function call here is a C++ type, but it actually is a interface. So it's like function create, function create closure. And here we have the connection function. So here this one is actually a polymorphic method that operate on different type of objects or closures. So we will apply that function call to the time. And right here we have a call foo class So this one is actually the one of the type of the operator implementation. So that is something that we can pass to the schedule add function. So we have this call foo. So we have the call foo. We have the call foo type 1 or call foo type 2. Okay. So here is a declaration of the construction of these. So this is say one CF as a call foo type function closure, and we run this one called polymorphic method is actually a dispatcher, and then you will use the call through function, and then now plus delay, and now is a function plus delay. You will get some time, so you will pass that time to this schedule add, and using the CF operator to it. And CF will go to here because it actually is a full type. So connector function is, or dispatcher function is polymorphic. And then the data object with the store data, and then this one is set up by this. So there are several different function closure can be passed to a dispatcher or connector function. And here we have the connection. We have the connect here, and here we have a connector function that's set up to this schedule function by schedule add function, and set up with the call through function. C++11 standard object closure encapsulating arguments. So it has a schedule add would then be defined to take object of this type function to be called with the 0 arguments at the first parameter, and the object CF passes in that first parameter will be declared as this. So you can using the binding function that will bind through with this parameter. That is a function. The bind function is a function to bind the through with that. Then this is a standard object closure, standard one that allows you to bind certain things with parameter to call through. Okay, so actually you can, instead of using the instance function, you can actually use the binding function in C++11, and you can actually use the dispatcher in the same way. Let's compare this a little bit. So previous one you set up by this instantiation of a call through class, and call through class you need to set up a separate call through class to do that. And the full object is actually a call through constructor with this. And this can be done if you bind the full class and then certain parameter put in there. It can be done with different way. So function object for table functions. So table of functions actually you can set up a long table, and then you can bind different way and then pass that parameter, and then it will get to the dispatcher, and dispatcher can actually being able to dispatch for different functions. So you can actually set up all the binding, and then you call that with different binding, and then perform that faster. So you actually can use a for each task, and then execute all the tasks. And the task actually is a table. Task is actually a table that actually bind different function type into task and execute one by one. So task is a vector, and you can think about vector as a table. You can think about vector as a table to run all the tasks. So using functional wrapper class function, and function is another way of doing those bindings. So here we have function. Let me see. Here we have a function 2, two different functions, and we have a class. And we actually have the function 3, 4, and function 3, 4 body over here. And then we actually set out the binding of the function to function 1. And function 2 is parameter as a function 2. So function 1, we use the binding, and then we run function 1. We will call this function 1. And when we call this function 1, it will say I'm using binding. And then we set out the binding between function 2 and the parameters. So we call this, it will give you 3 plus 5 equals 8. And then we actually create an object f of the ff type. So this f is actually a so-called the function closure. And there are 2 functions in there. So you actually here we have this f3 that bind to the function 3 for the ff function, ff object. And then you call function 3 with the parameter that actually will pass the first one and second one. This is the first argument and second argument. This is underline 1 and underline 2 are 2 parameter. So that 2 parameter actually will accept from 6 and 8 to here, and it will execute plus sign, and you get this. And then same thing for function 4. You pass this. Actually, the binding here, you bind the function 3 to function 4. So you actually pass this 6 and 8 over here, and you've got a subtraction. So you can download these 2 files to test out and figure out what functional wrapper and functional binding work. So in C++ language, right here dynamic binding, we have the bind function way. You can use typical the interface type for functional closure. You can use a functional object wrappers. These 3 are different way of providing the polymorphic dynamic running, dynamic binding mechanism. And you can download them to study for yourself. And here I just give you some introduction, but for details, there are a lot of detail that you need to learn. Mixin Inheritance, lecture 13. Mixin Inheritance is for the Java. So right here we have multiple inheritance versus mixin inheritance. So multiple inheritance is like C++ language. You can inherit multiple classes. Okay, for Python, so here you have C++ and Python. That actually allow you to inherit multiple inheritance. And mixin inheritance is you can only have one extension and multiple interface. So this one is class or object class, and here is interface. But because C++ doesn't support the idea of interface and object class, so it allows the multiple inheritance. And single inheritance is different. Instead of implement in this mixin inheritance, say for example, this one is like your D class. You can actually implement extend ABC 3 different class, and this one actually you actually will have D class extend A and then implement B and C. And this one single inheritance way is actually you have this one say A inherited by B and with some extensions of course, and then you inherit by C with some extra function as well, and then you can have D to actually implement C. So by doing this, these 3 all being included into D. That's the third way called single inheritance. So single inheritance also can get the feature from the inheritance tree. So these are different approach, but they can all solve the inheritance problem for inheriting multiple classes or class with interface. And Mixin inheritance is using the inheritance of the interface and classes. So classes can inherit from only one real parent. That's called Mixin inheritance. Can mix in any number of interfaces. Interface appear in Java, C#, Go, Ruby, Scala, Objective-C, Suite, IDA 2005. So it's a new feature for the Mixin inheritance. Has become the dominant approach because it's actually have better in terms of inheritance without confusion. And the function that allow multiple inheritance actually need to have a mechanism to resolve it. So here we have Windows 10 widget, so several different widget. The motivation for using interface actually is provide some capability or membership. Basically, interface has 2 main reasons for using interface. One is to provide some sort of capability. Capability means calling some function. Second is the membership, so you can actually provide the polymorphic methods. And we will show what is capability and what is membership over here. To ensure the requirement of windowing system, a language using Mixin inheritance allow programmer to define the interface that a class must provide in order for its object to be used in certain contexts. For widget, we report a system define a sortable object, graphical object, storage object. So these different things are different capability. And this can all be implemented by interfaces. And interfaces provide a function, but in terms of how to sort, how to graph, how to store, it can have different implementation for different objects. So an interface is a class that contains only abstract methods. Widget can implement the same interface that can perform the same methods of different implementation. So for example, like we want to actually perform some function that for this different widget, for example, to some window you want to enlarge, say, but you are operating the enlarge function for different objects. Then you actually need to implement the enlarge function for different widget. Those implement an enlargeable interface. So mixing interface into a derived class. So a class can have a multiple interface and one concrete class. And actually, this way you can actually set up the adapter design pattern. So you have adapter actually implement the target interface, and then you have adaptee, and that adaptee actually will have perform a special request. So a client function call this interface. I'm sorry, use this interface, and this interface actually is a interface reference, And that reference, because of polymorphic method, it will actually get the tease method to run by the polymorphism. So doing that, you adapt to certain features. So for example, you actually have something called say music player. A music player is actually MP. It's actually the interface, right? And then if you have an interface that play function, and that play may be a CD, maybe a tape or something, the music player will play different function for you. So here we have shape, and that actually is inherited by triangle and pentagon. And then there's an interface called color, and so it's inherited by these different color. And then the pentagon actually these inherit different geometry object, and also this green color, red color object that you can implement the interface. So you will have red color triangle, green color triangle, red color pentagon, green color pentagon, and the different scenes that's both shape and colored. And then you can actually use a green color triangle mix in the interface and the class. So you actually have different shape and different color, and you can actually instantiate with the concrete class below this. So implementation of interface in a language like Ruby, Objective-C, or Swift, which use dynamic method lookup, the method of an interface can be added to the method dictionary of any class. Method dictionary is actually the table or a map. So any context that require the interface type, the usual lookup mechanism will find appropriate method, and actually is the lookup for the vtable-like things. In a language with full or static typing, which pointer points to method expected to have the vtable offset that we talked about it before. So either you have the full interface, this actually has a dictionary or mapping, or you have a vtable. Two different ways to implement it. So here is a UML diagram for this figure 10.6. So you have a widget, you have name widget, and then augmented widget. Three different classes, and each widget may be sortable, may be graphable, may be storable, and each one has, you can have a sorted list, and those lists you have different sortable object, and name widget can be one of the sortable widget object for sorted list. So here is the widget's inheritance tree. Here is a sortable, that's a polymorphic container. Same thing for polymorphic broad window, polymorphic dictionary. And each one will include those sortable objects into the list as a container. So right here we have interfaces classes in Java. So implement the sortable object interface in name widget and the graphical object sortable object interface in augmented widget. We obtain the ability to pass object to those classes by doing this. So okay, so here let's see. Here we have class widget, and then interface. It has the interface sortable, interface graphable, storable. So actually here we have different. This is a container class. So it's just like the graph we just shown. So right here we have a dictionary class, and actually there is a polymorphic method called insert, and that insert accept the sort of storable object. So basically, this dictionary has a polymorphic method, and that actually you can do routine like this sortable insert and raw window add to window or dictionary insert. So these are different polymorphic methods that you can actually do. So dictionary insert is best storable object view of its parameter, and you will find parameter get store name. However, it's implemented by augmented widget and augment widget's view of the parameter. So we pass in a storable object, and then storable object will find the dynamic method of from the augmented uh, uh, widget, and there is a get sorted name. You run that copy. So the augmented object implements three different interfaces. There's no way that a single vtable can suffice. And the first entry cannot find the method of storable object, graphic object simultaneously. So actually you need to consult multiple tables because those table may not store in augmented widget, and instead it will store in the interfaces. But runtime you will try to find it. So compile time implementation of Mixin Inheritance. The most common solution to include 3 extra vtable pointer in each augmented widget object, one for each implemented interface. That's compile time implementation. Let's look at how it works. For each interface view, we can use pointer to the place within the object where supporting the vtable. So if we call dictionary.insert on a augmented widget W, whose address is currently R1, the compiler, which knows the offset of the W storable object vtable, we can add that to that and pass to insert. So basically, here is the calculation mechanism. You find a vtable address, and then actually calculate for the W address, and use that address to find the method address. So it's a indirect from your object to vtable, from vtable to indirect address, and then use the offset, and then to call the function. Okay, so that's that. So here we have the W object widget, in the original widget view, and then put in different view for the object, and then each because you inherit that, so those fields will be added in to an object, and then actually you will find different vtable. Okay, and then that's implement of the Mixin Inheritance. So object of class augmented widget contain 4 visible edges, 1 for the class itself and 3 for the interfaces. And the view of the object is passed to the interface routine pointing directly to relevant vtable. So in here, you will try to find the right table, and then say the one in the storable view, you will use, you have the R1 calculated as the widget pass offset to that, and then you find the entry from there and use that to find the R2. R2 actually, you actually from there, you call R2 plus 4. You go to basically find the method and then get the object, and the object is R3 is the calculation of the vtable of that. You get the method to run. So that's the mechanism we have in figure 10.7. Multiple inheritance. Multiple inheritance is different from Mixin inheritance, and it is always. So in C++, you can say this multiple inheritance. So you get all the members, but there is an ambiguity. So professor may have a print. A professor, a teacher, and researcher have different print function. But in order to resolve it, you better have the T print and the R print, so that it is better in different scope. And then through multiple inheritance, you have the virtual base class. In the usual case, you can inherit two classes, and that both derive from some other class B. And your implementation may include two copies of the B data field. So, and that's often fine. But one time you want a single copy of B, you can make B as a virtual base class. Okay, so here is the conclusion for object-oriented programming. Object-oriented programming is analog to real world. It is central to the object-oriented paradigm. You think in terms of real-world objects that interact to get things done. Many object-oriented languages are strictly sequential, but the model adapts well to the parallelism as well. That's for the concurrent programming. That's the next chapter we are talking about. And strict interpretation of the terms, it actually has the uniform data abstraction, that's encapsulation, and it has inheritance and the polymorphism. So three main topics here: encapsulation, inheritance, and polymorphism. For object-oriented programming are all defined in object-oriented programming. There are three important features of it. So we talk about all of these in this chapter. So it can be modularized, support event-driven programming, concurrent programming, distributed programming, and GUI. And in chapter 13, we will be covering this. And it's actually also doing this. And these two support graphic user interface. So it's actually good for the development for application in programming interface, foundation class, design framework. And lots of conflicts use of the term out the three of the term, and the object-oriented style available in many languages. Data abstraction is crucial. Inheritance required by most users. The term object-oriented, and certainly dynamic method binding is a matter of dispute. Someone like it, someone doesn't like it. And Smalltalk and Ruby are closer to ideal object-oriented programming language. And Smalltalk is historically the canonical object-oriented programming language. It has all three of the characteristics listed above. And to me, actually, currently for educational purpose, Java is the best educational language for object-oriented programming language, and C# is very similar to Java. So object-oriented programming language, basically, other languages are described as follows. And we have the Module 3 has single inheritance, and Java has Mixin inheritance. So 895 has this feature. I don't want to go into the detail for these all languages. And C++ or object-oriented is C++ object-oriented. The use of the right buzzwords has in multiple inheritance and generics, allow creation of user-defined classes that look just like built-in one. But C++ is not very pure. It has all low-level C stuff and has frames, a static type checking. So actually, C++ is a mixture of many things. It's not really the pure object-oriented programming language. And JavaScript is object-oriented. JavaScript is a functional, dynamic, interpreted, and not out-of-the-box object-oriented programming language. It doesn't have the OOP feature, but the OOP feature comes from the DOM documentation object model supported by HTML, and JavaScript had to support it. So the main difference between classical object-oriented programming language and JavaScript is that the OOP features are not provided by the language. It's by the DOM, by the HTML. So, summary, in the same category of question, is Prolog a logical language? Is Common Lisp functional? And however, to be more precise, Smalltalk is really pretty pure object OOP. Prolog is primarily logic-based. Common Lisp is largely functional. So this one is not pure. This one is primarily but not pure. And Smalltalk is pretty close OOP. And C++ can be used as in a object-oriented way. So that means from here to here, the definition is looser and looser, and C++ is actually a mixture of everything. It's a low-level, high-level language. Okay, thank you. Bye now.